RF communication to and from space satellites is obviously very important, so a lot of effort goes into optimizing the antenna systems for those communication links. But RF signal communication in, around, and through the satellite is also critical. If that RF signal doesn't make it from the power amplifier to the transmit antenna, your multi-million-dollar space mission could be a failure. That's why on today's Tech Chat, we'll be learning about selecting the right RF cable assemblies and suppliers for space applications. Welcome to Tech Chat, sponsored by Mouser Electronics, where we chat with engineering experts about the latest technical innovations that are shaping and reshaping our world. Today we welcome Maria Calia, Director of Space and Missiles at Times Microwave Systems, an Amphenol company. Welcome to Tech Chat, Maria.
Thank you. Really excited to be here today.
Great. So, Maria, what are you going to be talking about today in today's Tech Chat?
We're going to be talking about RF cable assemblies for space applications, especially in this new space era. It's become a more commercial world, and there is a lot of hype about 5G and LEO, and we'll be talking about some of the products that make the difference in these type of applications. Excellent.
Well, I'm excited to learn more about this topic, so let's get started. Before we dive into the technical portion of our discussion, could you give us an introduction to Times Microwave Systems?
Yes. Times Microwave Systems is part of Amphenol Corporation. Today is one of the largest interconnect groups in the world. Times itself is a very old company. It's been around since the 1940s. Funny fact, first warehouse for Times Micro was actually in Times Square, New York, hence the name. Obviously no longer there today. But we do have 70 plus years of expertise in designing and manufacturing high reliability cable, RF cable assemblies and products. We do have state-of-the-art capabilities in multiple facilities, 3 in the US. Headquarters is in Wallingford, Connecticut, but we have facilities in Florida, in Arizona. And then we also have international facilities in China, India, and Estonia. We have a highly technical team. So a lot of engineers, and we are focused on designing solutions for our customers.
Thanks for that overview. Can you give us some examples of space missions that are equipped with Times Microwave Systems components?
Yes. Times has actually extensive heritage in the space market on multiple missions, LEO, GEO, deep space, commercial constellations. So it's really varied, and it's due to the breadth of products that we can offer to the different applications. And Times actually doesn't only have products that support in space or onboard spacecraft, but we also offer products that can go into deep space exploration, on launchers, antennas, and SATCOM, and ground systems as well.
Are you seeing a significant increase in the demand for cable assemblies for low Earth orbit applications due to the massive growth in LEO satellite constellations like Starlink?
Absolutely. And there is more and more constellations coming up every day. It's definitely the orbit that's most popular now. What's different with the LEO satellites compared to a GEO, these satellites are smaller, so now you can build and launch a lot more of them. Starlink itself is thousands already in orbit, but there are several other constellations that are planned right now. And, these type of satellites are being launched for latency, so reduce the delay that there is in coverage of, internet communication, etc. And what's different as well is just the time from design to launch is really, that cycle has become a lot shorter with the LEO missions. So it's important to have products that are readily available and that someone can buy off the shelf to integrate to meet these demanding schedules.
Thanks for that background, Maria. Okay, so since this is a tech chat, now let's start talking technology.
So the first thing that people ask when we're talking about RF cables is, okay, how complicated can it be? It's only a cable. It's a cable, 2 connectors. It's going to go from point A to B. Actually can be pretty complicated because by definition, like we said, it goes from point A to B, but that point, between that point A and B, there could be multiple environments, and the cable could be crossing into different temperature ranges or going to a remote location. And so there are definitely additional considerations that we need to take into account. Is it the cable connecting boxes? How far are the boxes? Is the cable going to be exposed to radiation, temperature, and other environmental factors? And we do know that failure is costly in this world. So the space is the only environment where there is no opportunity to go fix it on site. Like you launch and you're done. If that fails, then you failed. So when we talk about space environment, there's definitely keywords or key terms that everybody in the market needs to be aware of. Terms like outgassing, multipaction, radiation, whiskering, vibration, and temperature. Basically, you think about the life of the RF cable from when it comes from ground, gets launched. So it has to withstand high level of vibrations before it even goes into space. And then it's going to be subjected to temperature exposure, radiation. There may be phenomena like multipaction when you have a power associated with the assembly. And then you have to worry about the outgassing of the materials. You don't want materials that are going to be outgassing, meaning material giving off particles that could potentially affect the instruments or damage lenses or, affect the life of the satellite. One thing that I always like to say when we talk about the various factors that affect an RF cable in space is make sure you're working with someone that understands all the variables, actually has access to materials and technology to support the various type of environments. There are standards in the industry that tell you how to make a cable, and there is standards that tell you how to make a connector, but there is no standard out in the industry that tells you how to put the two together. So that's really up to the individual manufacturer or supplier, and it's critical to the life of that cable and then supporting the mission or constellation that cable is going to go into.
Maria, multipaction is a term I've not heard before. Can you explain that for us?
Yes. So multipaction is a phenomena that occurs in vacuum when an RF cable is expected to perform at high power levels. When you have power applied into an RF cable, particles get excited inside, the temperature rises, and what happens is these particles, as they get excited, they can bounce back and forth into the cavities of mostly the RF connector. And two things can happen. These particles either get absorbed or they actually hit the cavity, and then there is additional particles that get ejected. So what the result could be if this phenomena keeps going on is you're going to increase the number of particles and you're going to generate a cloud inside that cavity that could potentially lead to a short. So there are ways and there are things that you can do to prevent. Number one is reduce the amount of cavities that could have a potential for this phenomena. There are definitely materials that are more prone to eject additional particles. So having the expertise in the RF connector design is key to mitigate for this phenomena.
Excellent. Thanks for that explanation.
So it is critical when you are selecting the RF cable in your application to understand what the trade-offs are. There can be trade-offs that have to do with the electrical performance and mechanical. So you have to understand what are the limiting factors in my application. Am I limited in space? If you're limited in space, you may be constrained in the size of the cable you can select, and therefore that's going to affect your electrical performance and what you can achieve in the physical limit or constraints that you have. You also have other limitation, potentially materials. We just discussed that with multipaction. You may be limited in the materials you can select. There are definitely other phenomena out there. LEO orbit, for example, is the orbit that's closest to Earth. And therefore, you may have residual oxygen called atomic oxygen, which could interact potentially with some of the materials in your RF cable construction. So understanding what those materials are and avoiding them is really important to the success of the mission. Temperature range, how hot and how cold is going to get in your application. How much radiation is that cable going to see? Typically with LEO application, we expect the radiation levels to be milder than in an orbit where you're further out from the Earth. And then vibration as well. That vibration environment now is dependent on, it's mission specific. And when we talk about the limitation on mechanical or the trade-off between a mechanical and electrical, you could have small diameter cables that can operate to high frequency. And this graph actually gives a very nice overview of what the trade-off says when you look at size, frequency, and then electrical performance. So the cables that will perform better electrically are actually the ones that have the lower loss profile there at the bottom of that plot. On the horizontal axis, we have the frequency. On the vertical axis, we have the loss of the cable. So you can see that the highest loss cable here is going to be a 140 diameter that has a phase stable dielectric. Then by comparison, the best performing cable in terms of loss is going to be one that's large in diameter, 8 millimeter in diameter, 0.3 inches. It's going to have the best loss, but also now it's going to have a larger band radius, meaning that to fit that cable in your system, you're going to have to route it, and you're going to need more space to route that cable when compared to a smaller diameter cable. There are definitely other factors that affect, especially in LEO, when you're smaller. Typically, we are looking at smaller diameter cable assemblies. It's rare to see something that's large in diameter, like the one that I just mentioned, the 8 millimeter. Of course, everybody would want the lowest loss cable, but practically, you may not be able to use it because, again, like you're constrained in size. And then also the larger cable is going to be heavier, less flexible. So again, all these are considerations that the designer has to take into account when he's selecting the cable. So an additional consideration here is the materials. We kind of touched on that on one of the previous slides. It's important to work with someone that has access to a lot of different materials. And this graph here gives an overview of why that's important. Times itself is probably one of the suppliers with the largest breadth of products, meaning we have different dielectrics that we work with in our cable constructions, and they do have different performing profile in terms of phase versus temperature. When is phase important? In applications where your response or delay time needs to be matched, it's critical that that response remains the same when the satellite is orbiting around the Earth and is crossing from a warm area into a cold area as it goes through its cycle. The materials of choice, or one of the standard dielectric materials in the industry, is PTFE, Teflon. Teflon is a great material for loss. It's what you see there as the blue and the red curves. Great for loss, but when it comes to phase, around ambient temperature, you see a sharp drop into the behavior of the phase. Again, if phase of delay doesn't matter, then great. But if delay is critical in the application, then you probably need to consider other types of dielectric materials, which are what we're showing there in the green and the purple. So the green in particular is our TF4 proprietary dielectric. It's phase stable versus temperature. And you can see it has a much gentler profile. It doesn't have a sharp drop like the PTFE does. And, the Teflon, that's what that sharp drop is actually called. And it definitely allows for much more precise control in the phase. We also have a non-plastic type dielectric, which is called SiO2, silicon dioxide. It's the purple on the graph. What's interesting about that material is the fact that the profile of the SiO2 is actually opposite to the phase track profile. So if you take the two and you combine them in line, meaning you have a cable assembly that's mated in line to an SiO2 assembly, you'll get an even flatter phase response.
I would assume that mission length and reliability expectations can vary a lot depending on the satellite orbit. Can you talk a little about the range of mission lengths that you see in the industry?
Yeah, that's definitely a factor, and there is variability there. For a LEO orbit, it could be as short as 30 days, but we're typically talking sometime between 1 and 5 years, depending on the size of the satellite and actually the purpose of the satellite. When we talk about GEO, which is the orbit that's further out, that's where we start seeing requirements for a 15-year life mission. So at that point, your radiation exposure becomes higher because it's longer tenure for the assemblies. But in general, for LEO, I would say that the products for a LEO applications are going to typically have different specifications than the ones for a high-rel GEO. So we do know that failure is not an option in space. As we said, when you launch a satellite, you cannot send someone up there and fix it if something is wrong. We have seen it actually in the news, even with the larger satellites, with some of the failures. We've seen large GEO fail, and then that mission is lost and it costs millions of dollars. For the LEO is a little bit different because, maybe the cost of the launch now has gone down and the size of the satellite is smaller, but there is still a cost associated with it. And, the trend in the industry is to pick materials that are off the shelf, cut based on automotive standards. That may not always be the answer. What you see is you still have a pretty significant rate. There are surveys out there that tell you that 17% of CubeSat failures are due to common subsystems, including the RF cables. So stressing again, it's important to work with someone that has access to technology and materials, and they can actually understand and even guide the designer in the selection of the proper cable for that application.
You mentioned CubeSats here. Since these require very light weights and lower costs compared to geosatellites, are you seeing any unique trends in cable specifically for these tiny satellites that operate in low orbits?
Yes, so the trend is smaller, definitely smaller cables because they do want lightweight, short runs because size of the satellite is very limited in a CubeSat. And then, ability to start routing the cable immediately, which brings us to the technology we can offer through the distribution channels. Getting into the technology a little bit more for the commercial space and the CubeSats that we were just talking about. The Instaband phase table that are highlighted here will be the two products that will probably be key. So we have Instaband is a PTFE dielectric. We briefly touched on that. It's the Teflons. It's a great dielectric for loss. If loss is the key requirement in the application, then that will probably be the product that will most likely work. What's unique about it is the cable and the connector attachment. You can see the connector is a very low profile, and we have a special clamp design that we apply. The center contact is soldered always for reliability. But what you can do here, you can start bending that cable right at the end of the connector, which is key in small spaces like in a CubeSat or something even smaller to be able to route the cable. If loss is not as important, but phase stability at temperature is important, then we have another product line that we can offer, which is the Instaband phase stable product. That one, it can also be routed right at the end of the connector. It has the similar attachment, but it's made with our proprietary TF4 dielectric. We also have lightweight options available for the small diameters, which can also help with saving on mass. And then for the bigger LEOs, where you have a little bit longer runs, we can offer the max gain space cable assemblies. And those, again, are going to be for typically longer runs. Diameter can vary between 2-3 millimeter diameter up to an 8 millimeter diameter, where with the Instaband, the largest diameters right now is the 090 or a 0.1 inch diameter, 2 millimeters. These are considered standard products for the industry. You have the summary of specs or typical environment that we see in this type of applications. So the assemblies are rated up to 30 megareds of radiation. The temperature range is -90 to +150. We offer clean room manufacturing class 100,000 with COC. These assemblies are obviously TVAC compatible, low outgassing per industry standards. We do 100% visual and baseline electrical. And again, this set of specs we have developed based on our expertise and understanding of what the market needs to ensure a successful mission. This just gives you a better idea of the product differentiation and how to select the right product in the application. So on the x-axis, you have the frequency. On the y-axis, you have your run size. So as discussed, smaller diameter, shorter runs, probably somewhere inside the box by definition, higher frequency. And then for the max gain family, which is at the top, they're typically outside the box. So box to box connections. They're lower loss cables because your diameter is getting bigger. And by definition, they're going to be lower loss. It again depends what's more important. So always ask the question, is loss or is phase more important? Where is it going? Is it inside a box? Is it box to box? That will help determine which product family and which product fits best.
Maria, as we near the end of today's Tech Chat, are there any final thoughts that you would like to share with our audience today?
Yes. So final thoughts, absolutely. So again, I cannot stress enough, make sure that you're working with someone that has access to materials and a large breadth of products, and do not settle on performance. One of the things that I often see out there is designers do not worry about the RF cables until the very end. They're selecting all the other components, which may be your PC boards, can be your boxes, your connectors on the boxes. And then by the end of that cycle, you're kind of stuck with your distances between boxes may be tight. And now, you have to talk about, I need a short run, but, I don't have enough time to bend. I may need a super low profile connectors. Again, these are things that cannot be overlooked. Talk to your supplier, make sure, engage them early. So that they understand what you're trying to accomplish, and they can actually help you fit the best solution, and doesn't have to be expensive. That's the other part. It may end up being more expensive at the end if you don't give it enough thought in the beginning.
Before we sign off today, we want to thank our sponsor, Mouse Electronics. If you're looking to purchase any of these great Times Microwave System products, please head over to Mouser.com to help them continue to support educational presentations like this one. And join us again next time on Tech Chat, where we chat with leading technical experts like Maria Calia from industry-leading innovators like Amphenol's Times Microwave Systems, who are changing our world every day.